All right, I will begin with a word of prayer. Dear Father, we thank you for this day again, Lord. I thank you for the students. Just ask you to help us use this time wisely, Lord. In your name I pray. Amen. All right, so let me make sure I say what I was going to say about the quiz before I forget. So, again, the in-class problem was a little bit tough. Although I think the reason it was tough, I wouldn't say that I wouldn't rule this out for the final entirely, because this problem only becomes really, really difficult if you insist on doing it the same way I was doing it in the in-class example that led up to it, right? If you just have the common sense thought, oh, wait a minute, I should calculate the area of the inner loop and subtract it from the area of the outer loop, then it's not that bad. It's just the integration's a mess, But the setup isn't that bad, really. Goodness gracious, grading the quiz, so many, maybe not you guys, I don't know, I can't remember. I try to forget. But there are many people who had not settled in their mind how to calculate arc length with respect to, like a polar graph or something. And so, and you can view this as a special case of the more general. If you have a parametrized curve, right, what's the arc length? So integral over the parameter domain, say t1 to t2, square root of, say, x dot squared plus y dot squared dt, right? Where x dot dx dt and y dot is dy dt. So in the special case, now we also worked out that is the integral over t1 to t2 square root of r dot squared plus r squared theta dot squared. That was a homework problem. Because what's inside is the speed squared, right? So that would be the formula for arc length that would be useful for a parametrized polar curve, that formulation. But you can see the standard formula as coming from this in a very sort of obvious special case, which is just what? Choose t equal to what? In this formula, we're thinking of the parameter actually just being the polar angle, right? So when you put t equals to theta, theta dot's just 1 because it's d theta. So this formula simplifies to dr d theta squared plus r squared, which is what we use for the standard arc length of a polar graph. But these are not disconnected ideas. If you understand the formula for arc length in the parametric setting, if you really understand this formula, you can derive all the other ones from it. Or you could just memorize them all separately as if they're just unconnected events. It's up to you. But I will tell you this, at some point in your mathematical career, memorization will fail you. For most people, that happens at Calc 2. Most people can memorize their way through Calc 1 just fine. But Calc 2, it's too much. I still have some linear algebra students who, after the test, were like, I should have memorized that. I should have memorized that proof. I'm like, no, you shouldn't. I don't tell them. I mean, I don't even say it to them, because at this point, like, if they haven't, I just feel like I've told them before, I feel like it's rude. If you tell somebody something and they don't listen to you and you keep telling it to them, it's kind of belligerent, They obviously they're adults, they've made their choice in life, what can I say? But you should not try to memorize everything. You should try to understand everything, In the end, your life is much easier. Now, okay, so I don't want, this was, ugh. Let me go on here. This is what I want to get to. I think of all the problems on the quiz, the take-home part of the quiz, I think pretty much everybody did this one nearly right, or exactly right. So I'm pretty happy with this one. And most people had this, give or take. I mean, there were a few people who didn't close the second loop or something, who weren't quite. I mean, there comes a point where I'll take a point off. Like if your outer loop ends over here or something, like I'm going to take a point off. I will allow. I mean, if they were vastly different scales and they were tilted one or the other, I probably didn't even care that much. But like the loops should close. I mean, I do have some standards for graphing. Yeah. But it's negative. The radius is negative, so it would be down there, except that it's negative, so it flips it over. Ah, I remember yours. Now, problem 3, I derived a formula for the slope in polar coordinates, you know. But I don't know, I just find myself going back to base principles in these problems. It's about the same difference, I don't know. So we have x equals to this, we have y equals to that, that's the x velocity, that's the y velocity. The point we're interested in is t equals to square root pi. I plug it in, I get -1, I get -2 pi. So the slope is 2 pi. This is the place I wanted to gripe at you guys about. So what were the instructions to the, what were the instructions here? See, this is the annoying thing, is I didn't print out the instructions, so I got to go back to the other PDF. Sorry about that. I said, I gave you the polar parametric equations, quote unquote. I said, find the equation of the tangent line. The equation of the tangent line to the point C. So I saw people write some really weird stuff for the answer. And like, I think it shows partial understanding, right? But the equation for the tangent line should be just that. It should be an equation for the tangent line. In other words, something of the form give or take y equals mx plus b kind of thing, you know? That doesn't have to be that. You could do the y equals to, you know, y1 plus m times x minus x1. This would give you a line with slope m and point x1, x1, y1, you know? This is what I usually use to write the equation of a line, because I often in calculus have the slope and I'm trying to write down. And so that's what I did here. I figured out the slope was 2 pi. And then I figured out that the point of tangency was minus root pi 0. And so that's what led me to write this, because the y1 is 0 here. And so, but it should have been that. What I saw people write, and this is concerning to me, was something like this. I can't even remember what you guys wrote. But it was something along the lines of, and this is paraphrasing, so I don't remember what exactly you guys did. It might have been like this times t plus 2 pi. And like, so in this course, it's understandable that you might write such a thing because, well, we haven't spent a lot of time on vectors. But this will offend your 231 professor. See, because what this is the sum of a vector and a scalar. This is not allowed. And I saw this on not 1, not 2, not 3, not 4, not 5. Something like 10 of you wrote this. Something like this. You had a vector plus 2 pi. I can only assume that people must have been working together. Yes? I hope. I don't know. I'm not sure. But I took off 3 because that's like a significantly wrong thing to write. Now, if I wanted to write the parameterization for the tangent line, what would I do? The parameterization. So, on the one hand, this is the equation for the tangent line. If I wanted to parameterize the tangent line, I could do this. Say L of t equals to the point of tangency, which was what? Minus root pi 0. And then plus t times the tangent vector. The tangent vector here would just be like x dot of root pi, y dot of root pi, which would be minus 1, 2 pi. Minus 2 pi, rather. Did I get that right? Yeah. So that would be a parameterization for the tangent line. If I wanted the parameterization of the colliding tangent line, what would that be? I know it's been a while since we talked about that, but what would I do? I do point of tangency, and then I have to shift this to the time where it, yeah, t minus root pi, right? But again, it's a sum of vectors, something like that. Those would be the parameterizations of the tangent line. These will become important to you in Calculus 3, all right? The equation of tangent line stops being an interesting concept for us in Calc 3. But, all right. Anyway, that was the big to-do I was talking about in the announcement. You're like, well, that's kind of underwhelming. Fine. Yeah, because you guys were mostly right. You just wrote something that just graded against me. All right. So with that, let me transition over here to the final battle, which sadly I do not have graded yet, but I will be, as soon as I have them graded for pickup, I'll tell you guys. It's not there yet. I'm disappointed in myself for not writing the instructions for problem 1 a little bit differently. I should have said, find the Cartesian equation of the curve and identify the curve, right? So to identify the curve is to complete the square and notice, hey, it's a circle centered at 1, -1 with radius √2, right? This is something we talked about like the first week, right? Any questions? So, oh no? Oh, okay. So this is like, you know, how do you convert a polar equation to a Cartesian equation? When I see something like that, I usually look for ways to create r sine theta and r cosine theta because I know that those are y and x respectively. And I know if I can change r to r squared, well, r squared is x squared plus y squared. Those are my usual moves in this game. This one, let's try graphing that in Desmos for a second.
Yeah, I was going to say, I attempted this one. I attempted that one.
I don't think I even attempted it. It's been a really long time.
Well, I got to a point where it just like didn't make any sense because point 2, 2, if you think of that point in a polar graph situation, like r is equal to.
All right, what were the parametric polar equations? It was r equals to 4 sine t, and theta equal to, what was it? Oh, you know what? I'm probably going to have to do, I think I'm going to have to do it like this. 4 sine t, and then it's cosine of what was the theta? It was inverse tangent.
You could write arc tangent.
Thank you. And I think it was t, 2t to the 5th. Minus t squared.
Yeah, what made you think, man, I need an infrared scanner in my life?
Because of people like you.
Am I hot?
Come on. Where?
Wow, that looks not happy.
Ah.
So, if you're combining, if you're putting in a parameterized curve, and don't you have one side, comma, the other side?
Yeah, I'm working on it. That's what I'm trying for.
The intro, like South Park, the intro song at the very end, like "Come Meet My Friends."
Those are fancy. Wow.
It sounds just like.
Does he have one? Look at them. They're pretty. Sounds like they get the end.
An episode just doing my homework.
Keep forward. I got the. I only watched. Is the
I don't really normally, but
Oh, that's, dang it.
I was doing my homework and
It's a dot.
We're getting somewhere.
How do I?
Drag your T slider. Does that like trace out shape?
Yeah, it does, but I want it to.
That's fun.
Oh, that's cool. That is.
So basically, it goes in the line y equals x.
I guess. Are you translating for Desmos? Yes. This is what Desmos means. Just having a hard time saying it.
Huh. Well, I thought.
Basically, what they can conclude is this is y equals x.
Very, very complicated way to write y equals x.
Isn't that the mission, except it was the other way? No one problem in the mission where we're
Oh,
like,
yeah, I
it's
know.
just a line.
Oh, yeah, the line between the area.
Yeah.
Area of the triangle.
Sadly illustrated here. I love the parenthetical comments here.
Oh, same. It makes studying so much fun.
Okay.
Is that, wait,
I love the official
I wanted you to solve for t.
Of course, there are other ways to derive.
All right. So, what I was hoping to do, and I apparently have forgotten how to plot parametric curves in Desmos today. I don't know what's wrong with me. I thought I had plotted parametric curves in Desmos before, hadn't we?
yeah.
I mean, did we have we always animated them?
Yeah. And then we got his like.
I guess we animated it was the thing though, and I really want to look at not the animation of it, but the whole thing, because I think that the point I gave you is not on the curve. But when I was just looking at it, it looked like it might be. But let me break it down for you. I'll break it down for you what happened there. Basically, problem 2 is going to get thrown out. Long story short. Yeah.
Yeah. So I don't know if I'm thinking about it right because I was in my attempt. I just was thinking, well, if there's a point that's on that parameterized curve, then if you turn that 2.22 into an r and theta value,
Right.
and then plug it in,
Yes.
shouldn't you get a t value
That was the intent, and I'll explain what went wrong when we get back to that problem. But we'll get back to it in just a second. Yeah.
So it's like this math I would get our potential to our final. Like I know it's cumulative, but like is that like the level?
Am I supposed to be turning the camera?
No, I think I've got it set so we can see everything. I'll check again, but
I just realized that.
no. I tried to set it up here so you can see the screen and then a little bit more. I think we should be okay. I do think that the final battle gives you some sort of indication of the comprehensiveness of the final in some sense, but I mean it's not all inclusive, but I think hopefully it's given you some sense of the fact that it's usually the case that I overemphasize integration and I tend to overemphasize series a little bit. I tend to underemphasize convergence, divergence, and I mean there's going to be some differential equation. I don't know, but I shouldn't say too much because whenever I do, I regret it. The final is comprehensive, let's just say that. So, anyway, so this one is a pretty standard problem, right? Graph of 6 sine 3 theta. And I always draw too much of the r theta graph and then come to terms with the fact that I didn't need all this because I already got this, that, and that from this one, and that one. And then I just start retracing my steps. Got to get some light out. Anyway, so there you go. Now to set up an integral that provides the arc length of the curve, I say 3 times the length of the first petal is the easiest way to do it. Of course, you could just as well have, what you couldn't do here is integrate from 0 to 2 pi, and that's the thing students will do wrong. You guys will just assume it goes from 0 to 2 pi to get a full cycle, and it's not the case here. In fact, 0 to pi would do it if you didn't put the 3 here. Right? And then again, you know, there's a square root. It comes back to the thing I erased down here a second ago, you know. R is 6 sine theta, dr d theta is 18. 18 squared is 324. All right. Area outside r equals to 3 and within the polar graph, I'll do on a following page. I think it works out to this. actually next page. One more problem on this page that I have solved because it was, not a lot of work. Remember first week, second week somewhere in there, we learned how to parameterize conic sections. For example, this circle, which is centered at 3, 0, and has radius the square root of 34. I meant to add 25 and set it equal to 0. Then the radius would have worked out to 25 minus 9. So it had radius 4. Yeah. Fortunately, it's not a wrong problem. It's not like the one we're about to talk about, which was the one I was trying to vainly graph in Desmos a second ago. All right, so now, I don't want you to ignore problem 2. I want you to ignore one aspect of problem 2. The larger idea of problem 2 is important. You need to be able to find, the graph. You need to be able to find the equation of the tangent line to a polar graph, right? That hasn't been tested on yet, and it has to be tested on the final, most likely, right? So it's not usually worth a lot, but it's there usually. So again, here's the this is not a polar graph, though. This is actually a parametrized polar curve. And so, Hannah, this is all your fault because you were eliminating time and changing it to a polar graph. I wanted to create an example where that was impossible. That's why I did this. This is all on you. See, because I figured there's no earthly way you could solve this for t. Right? So you have to take this. You have to approach it in the way that I'm doing and look at it in a parametric sense. So, but as is often the case when I try to make an example to help a student understand what's going on, I make it too horrible, right? And then, well, let me show you what happened. So this is the derivative written in the kind of sneakiest way I can think of. This is the derivative of the inside function divided by 1 plus the argument squared. So I'm taking inverse tangent of this, but this is tangent theta. So anyway, getting to the point here finally. Sorry, I'm spending entirely too much time on this, but it's my own stupid fault. So my hope was that you'd go, oh, well, if we're at 2, 2, that means theta is pi over 4. Great. And so that means that tangent of theta is equal to 1. And then 1 is equal to 2t to the 5th minus t squared, at which point you might see that there's an easy solution to see here, right? Whenever you're presented with some sort of ugly equation in a test or in homework or something, you should always at least check 0, 1, minus 1. It takes you almost no time to check those. And if you try 1, it works. Yeah. So t equals to 1 is a solution. Unfortunately, that makes r equals to 4 sine 1, which does not produce 2, 2, because r cosine theta is then 4 sine 1 times cosine pi over 4, which is 4 sine 1 over root 2, which is not equal to 2, which is what it should be, dx. See, I figured out what it is. Mid-invention, I confused the t and the theta. I was thinking that because theta was pi over 4, I would plug that pi over 4 into sine, and then that would make the root 2 over root 2 be 4 over 2 be 2. So this was the confusion which made the problem horrible. And I'm not convinced at the moment that that point is even on the curve, although it seemed like when I was just animating it that it was. In fact, it seemed like it is at t equals to 1 in my animation, but I don't trust what I put in yet, so let's just go on. I will, I mean, obviously I would not give you a problem on the final where you have to use Desmos to find out what it looks like, But the larger point here, and this is what I mean, I don't want you to just ignore this problem. I want you to ignore the problem of specifically finding the t naught, because that might not be possible here. At least I don't think it is. So to calculate dy dx, we take the y derivative at t naught, we take the x derivative at t naught, that gives us the slope, and then we create the equation of the line. Because I gave you that the point of tangency was 2, 2, so we can create the equation of the line like that. So in summary, the problem on the take-home quiz was a better problem. That's kind of the same thing. But it was a worse problem because it allowed you guys to dodge doing it the correct way, because you could solve for t and change it to a polar graph, which is really not what you should be doing here. It's impossible to do here. There's got to be a middle ground, a problem which is not doable as a polar graph and yet not this horrible. But I haven't found that middle problem yet. Maybe I'll find it for the final.
Could you just in just a couple sentences, explain how you would run through this problem if everything worked? So you would take the derivative of
Just
dy or dt and then dx of it?
I would, yeah, I mean, I would find the parameter, which gives me 2, 2. I call that t naught. I would then plug it into x dot and y dot. The x dot at that time divided by y dot at that time would give me the slope. And then I've got a slope, I got a point, I can write down the equation of the tangent line. The thing I couldn't do in this solution is find the time which we reach that point.
Okay, so you got y dot by taking y plus r sin theta and plugging in the equation.
Yeah.
Y dot is just
dy
on the notation.
dt. Mm-hmm. Mm-hmm. So let me go on. Again, if you're confused about this one, focus your attention back on, so if you did not, what I'm trying to say is, if you go back here to problem 3 on the take-home part of the quiz, this is the same problem with a less complicated parameterization. All right? So if the thing we were just looking at is confusing, focus your attention on this one. And notice how I'm doing this problem. Don't switch it to a polar graph, because you might not be able to. All right, I've said it. All right. Now here's the area calculation for problem 3. You're supposed to find the area outside the radius 3 circle and inside the 6 sine 3 theta curve. So if you look at that, it's like the outer edge of 3 petals. And so I think the laziest way to do it is to just multiply this area times 6, because there's like 3 of these. In each one of those, there's 2 by symmetry. That's half of the area in this petal, chop petal. And so that's this integral. And of course, you have to find what that theta 1 is, which is not obvious. But if you set 3 equal to 6 sine 3 theta, that should give you the intersection of the petal and the circle of radius 3, right? And so when I worked that out, that gave me 3 theta is pi over 6, which told me theta 1 is pi over 18. And then past that, it's just relatively straightforward integration. Remember, it's 1/2 outer radius squared minus inner radius squared to calculate polar area, right? Make sure you have settled in your mind the difference between calculating the area in terms of polars versus calculating arc length in terms of polars. These are quite different, right? And if you don't have those clear in your mind, and you take a problem and you try to do it one way where it's supposed to be done the other way, it will likely make it impossible. All right? Let's see here. So some of you are probably wondering about problem 5. I'll come back to that in just a second. Set up the partial fractions decomposition. So, again, the point of the final battle rather, is to prepare you for the final exam in part, right? And so, this is x squared minus 9 times x squared plus 9. And I'd written a 9 here because I'm an idiot. So I tried to change it to a 3. I need to get some white out again. Sorry about that. So this is x squared minus 9, which factors the difference of perfect squares, right? X minus 3x plus 3x squared plus 9, that's irreducible. And there's your partial fractions. This one, you can factor out x squared. This is irreducible. It's complete the square. You got a sum of squares, right? So this one here, another acceptable answer would have been cx plus d divided by that. You know, that's also considered partial fractions. The reason I write it this way is if you're actually going to do the integral, this would set you up for an easy integral. Yeah.
So if the power in the numerator is bigger than the power in the denominator, should I long that?
Mm-hmm. Right.
But you don't have to do that if you just set up.
What? Oh, man, I forgot. Oh, curses. No, you're right. I got to do long division before I do this. Ah, man. Son of a gun. But after you do the long division, this is still the partial fractions plus a polynomial of order 3. It should be this plus a cubic, which I can find. Yes. We put our hands up in the air. Yes, very good, very good. Okay, so indeedly, yes. Oh, I'm sorry. So this needs to be corrected. Fortunately, you guys are the only ones that have seen it yet. So if I edit this out, no one will never know. But I'll leave it in because it's funny. So, you know, students like to see me make mistakes, I think. So I'm thinking of, like, in future classes instituting like a challenge protocol. Like if you do bad on a test, you can challenge me to like a mono math battle of some sort. I should have some sort of handicap, and it should be some sort of problem prepared by another professor. You know?
Like physical handicap?
And it should be like, it should be,
Someone has to read the problems to you and to tell them what to do with the numbers.
and like it should be, but it shouldn't be, it should be dangerous, right? Like it could make your situation worse. You know? I haven't worked out the details yet. This is something I'm thinking about.
How about there's like 7 problems, and like whatever you get like over 5 will be added to your grade, but if you get under 5 will be subtracted to your grade.
Hmm.
That's cool. Or else
I've
like,
always-
out of 10 maybe.
I've always thought the idea that you could have negative partial credit on a test is intriguing. Like, what if you did so bad on a test that it took points off from other things? Maybe there's a mistake that you can make on a test that's so horrible that you should lose points from homework or something, right?
I would have a 0.
What kind of mistake would that do? Would that be like the vector mistake?
I-
On the first test, really
I kn-
like a 60 and then
I'd know it when I saw it. No, actually, I had a student who transferred here from Penn State, and there is some professor there who's doing that. Actually, it's a true story. If I trust that student. Oh, wait a minute. Do I trust that student? I don't know. Debatable. Now, look. Hey, I figured out long division. I mean, I figured out the issue on this one because it was, for some reason, I was too busy making 8, 6, 7, 5, 3, 0, 9 here that I neglected to actually do the math. But let's see here. You didn't even notice, did you? Anybody notice?
no one saw that.
See, there's 0. There's 0 x squareds. That's where the 0 is.
8, 6, 7, 5, 3, 0, 9. Yeah.
Because there's 0 x squareds. You gotta use your magic. I should have.
Song?
That's right. Let's see here. So this one was a repeated. So you notice that this is much like that. When we have a repeated linear factor, we have to do this plus that, right? That's the partial fractions. All right. Moving along, moving along. What?
Tommy
I was just trying to. I
While
didn't
they're
know
listening,
that
he's like,
I
I'm
was
studying
the one
calculus.
comes from
It's not a good song, so you're fine. It's just one of those songs like everyone
talks
knows.
that you just have a common denominator.
If it's popular,
Yeah.
It was from like
Just trying to
way back.
remember what I was doing.
okay.
The
That's even I was-
the difference in the partial fractions
The
is
middle part is straight
if
edge
it-
and more like sweaters.
No, it was from like.
if it corresponds to a quadratic which cannot be factored over the reals, then that gives you something that integrates to like natural log of something, natural log of a quadratic, and inverse tangent of something. On the other hand, if it's 1 over a linear factor squared, something like x plus 1 squared, then it gives you something like a over x plus 1 plus b over x plus 1 squared. The 1 over x plus 1 integrates to like log of absolute value of x plus 1. The 1 over x plus 1 squared integrates to like minus 1 over x plus 1. So the integrals are quite different, and the partial fractions is different because there's a distinction algebraically between a quadratic which can be factored versus one which cannot over the reals. But this problem 5, if you go back to the start, maybe you can anticipate what's going to happen. Let's think about this for just a second. So what does this equation say? What is this square root? This is the distance from where? From xy to 0 minus c. This is the distance from xy to 0c. So what this equation says is that the difference of that distance and that distance to a common point xy is held constant at 2a. If we take the collection of points for which the difference of the distance between two fixed focal points is held constant, what is that curve called? What if we put a plus here instead? If you take the sum of the distances between two fixed focal points held constant, what kind of curve is that? That's an ellipse. This is a hyperbola. Yeah. Yeah.
That is so subtle.
And you can work it out. So eliminate the radical, square both sides. Algebra. Algebra. Eliminate the radical again, square it again. Stuff cancels. You group things. You use the b that I gave you. And it simplifies to that. This is a great opportunity to say, oh my gosh. Again, most certainly a joke made by someone who should obviously be a math major. I cannot. Who's your genetics professor? I will pay for your grades to be worse than they should be. See what I can do. You should be very suspicious if I try to strike up a conversation with you the next semester saying, so what confuses you in genetics? Like, be very wary of this conversation. Because I will then take that information to your professor and see if I can influence him. Or her. You know her. It's 2019. I won't sell it like that. I'll just sell it like, yeah, the recombinant blah, 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 blah. You know, it's really interesting. Whatever it is you do, I don't know. The D. If you're confused about the N, then I'll try to make the test about the N. If you're confused about the D, I'll try to make the test about the D. Yeah, I don't know. That's pretty much, I mean, that's my level of understanding of DNA. It's like there's a D, there's an N, and there's some sort of something. There you go. Yeah. So yeah. Now I have not looked at all of the different math, the solutions yet. But if anybody got this, I will be very surprised. Because it's just, look, this algebra is not hard, right? But it requires like calm persistence, which is very difficult to maintain during the time pressure of a math battle when there are 19 problems to do.
So are there going to be questions on the final that you're going to be like, I'm surprised that anyone gets this right?
I always try to put something like that on the final, not all of them. See, you guys think about tests in terms of what grade you're going to get in this class.
Obviously.
It's fine. But I use tests for several purposes. Yes, one is to determine your grade, but I will sometimes put a question that really won't determine your grade or not. But you solving it and doing it well will determine that I can write a good letter for you later. You know, like sometimes there's a problem on a test, which I'm putting there, so if a student solves it, I can say, this student solved this problem on this test. And, you know, only like 1 out of every 500 students can do this. You should hire this person. This is why I do this, is so I have something to talk about in letters later.
Can you just take it off of mine because I know it's not me?
You don't, you're like, I don't want a letter, just give me the test with no future. I see here. or whatever. Who knows? Maybe I'll be too busy to create this horrible problem. I'm
I am not going to get that hard problem. Okay. I would not have had the foresight to be like, oh, that's the distance held constant between 2 points. Like,
But how many of you had never seen that derivation? Right. That's something that absolutely should be covered in college algebra when you're talking about conic sections, or wherever you talked about conic sections for the first time. Was that in here? Seen it? Right, but algebra 2, it should really be done there, right? Like, there's a similar derivation of parabola, ellipse, and hyperbola. And depending whether you make it open vertically or horizontally, it puts things slightly different. But it's algebra just like I showed you in every case. Now this one here was nice in the sense that that cancels with that. So we can like reduce the problem a little bit off the bat. And so I got, this was my partial fractions decomposition. By the way, there's a common mistake students make, which is they think everything's set up and nothing is actually work it out. But the integral, you can't just go, that, I'm done. This is a mistake people make a lot of times on the final. If you're like, you get a sense of accomplishment, right? You're like, I found this. I know I'm right. Put a box around it. Go on, right? But that's not the end. You have not integrated at that point. You must go on. You must finish the problem. So the next thing you got to do is actually find the A, B, and C. And then after that, you still have to integrate in this problem, right? So there it is. Now, so once I have a chance to correct my mistakes and a few things, I'll post this a little bit later today, hopefully. Did you guys get this one? Or was I too sneaky? You got it? Hooray! So yeah, I mean, this one you kind of have to see through my, we might have a homework problem like this, I think. So if we multiply by e to the x over e to the x, then you have a quadratic and e to the x down here. You can make a u substitution, partial fractions, you're done. There's probably another way to do this, I don't know. Let's see here. Now, early on, back when we were doing integration, I taught trig substitution, right? But I also taught hyperbolic substitution. And this was the principal example which motivates the need for hyperbolic substitution in calculus, is because this problem, if you were to do a trig substitution, lands you to a secant cubed, which is just unpleasant. On the other hand, if we make an x plus 3 is 2 sinh beta substitution, we just end up with the integral of 4 cos squared, which is pretty easy to do. So there's that. So sine cubed, this one comes up a lot in Calc 3. And it's just, you know, this is, I don't know, probably if I looked at 10 finals in Calc 2 I've given, it's probably on 7 of them. This or something like it. I mean, it's very common. Also, I would tend to put it in the final of Calc 1 too here, because we do cover this kind of integration in Calc 1 here, right? But a lot of you have forgotten it by the time you get here, and it's important, so we need to make sure we keep drilling integrals of powers of sine and cosine. Now, this one, part B, I would say is a next level problem. To me, this one is harder because it requires a deeper trigonometry. Like some way or the other, you need to know that this product of sine and cosine 3 theta is 1/2 the difference of sine 4 theta and sine 2 theta. Now, up here I've derived it with imaginary exponentials. So you could, I don't know, I mean, you could memorize the requisite trig identities if you want to do that instead, but some way or another you need to find a way to deal with these sorts of problems. You got it? Yeah, okay. So minus 1/8. Ah. Yeah, they should have been mission. I should have had it in mission 1. I think that's right. And unfortunately, that's as far as I got. So past this, I will be working these out and posting them a little bit later. Is there any particular one you'd like to talk about? I can say in words what to do here. It'd probably be good for me to do problem 13, right? Problem 13. Sine of x squared about 0. The first three non-trivial terms will be theta minus 1/6 theta cubed plus 1 over 120 theta to the fifth plus dot 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 dot. Here theta is x squared. So this gives me x squared minus 1/6 x to the sixth, can't say words, 1 over 120 x to the 10th plus dot 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 dot. There you go. First three non-trivial terms. That's doesn't have to be harder than that. You guys make this way harder than it is so many times. It's actually very, very simple. I hope I finally sold this to you as being simple. Maybe. The next one is not quite as simple, about x equals to 1. So we could do recentering. I'll do recentering for a second. Right, so that's x minus 1 plus 1. And so what I'm trying to get at here is after I get done doing this, I think it's so much trouble. It's so much trouble what I'm doing that it's just almost not worth it to do the recentering trick for this one. I think this one is probably easier just to do direct application of Taylor's theorem. Probably. So let me do that. Because the recentering is just unpleasant. And I'm only looking for 3 terms. So like recentering will shine more if I'm looking for like 20 terms or if I'm looking for a general formula or something that might be. But this is just, I think it's a law of diminishing returns, so to speak. So instead I'll just use Taylor's theorem on this one. F of 1 is e cubed. Oh, wait a minute. E to the 5th? What's f prime of x? Product rule, right? E to the 2x plus 3 plus 2x e to the 2x plus 3, which I probably should write as e to the 2x plus 3 times 1 plus 2x, yeah? So that gives me f prime of 1 is what? 3 e to the 5? And then I need 3 non-trivial terms, right? So I need one more derivative, f prime prime of x, and that's going to give me e to the, I'm going to do it in my head, e to the 2x plus 3. When I differentiate this, it gives me, first of all, 2 times that. Well, excuse me, yeah, so 2 times that, which gives me a 2 plus 4x, and then from that plus 2. So I think, if I haven't made a mistake, f prime prime of 1 would be 8 e to the 5. Now that I have the value of the function at 1, the value of the derivative at 1, the second derivative at 1, those are all non-trivial, then I can use Taylor's theorem to find the first 3 non-trivial terms. Don't forget the half on f prime prime. Don't forget the plus dot dot dot, and so that would be e to the 5th plus 3 e to the 5 times x minus 1 plus 1/2, well, 4 e to the 5 times x minus 1 squared. And that should be it. How about part C? What would you do there? That is binomial, right? I would go binomial on that one. No singing in the final. Let's see here. Is that Animaniacs? It feels like Animaniacs.
That's from Pirates of Penzance.
Pirates of what?
Penzance in operetta.
Oh.
It's that song I am the very modern.
I don't know where I know that from, but not that.
Well, they sing it in one version.
That would be it. VeggieTales, it would be VeggieTales. So this one, factor out the 32. Indeed, that becomes 2, 1/2, right? So you've got x squared over 2, and then 1 minus 1/5 x cubed over 32. So what I'm using is 1 plus u to the k is 1 plus ku plus 1/2 k times k minus 1 u squared binomial series. That times x squared over 2. So the next thing would be plus 1/5 times minus times 4/5 times x cubed over 32 to squared plus dot 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 close parentheses, and then you have to multiply through. So like it's x squared over 2 minus 1 over 320 x to the 5th plus 1 over 200 x to the 6th, maybe. I might have lost a 2 in there somewhere, though. Maybe over 400. I'm not sure about the third term, but multiply that out, that's it. Yeah. Do you agree with me that binomial series is the right way to do this? Like, what if you tried direct Taylor theorem here? Yeah. It's awful. Yeah. I put a half out the front. I put.
I mean, on the third term.
Oh yes. There's supposed to be a half here. Thank you.
I don't know, that half has been missing in a few different places
Uh-oh.
on the occasion.
Yep.
Zach just asked me what finals we have tomorrow because we have all the same classes. We should have I'll tell him that he said we have this tomorrow.
Tell them the Calc 2 final is. Tell Zach that the Calc 2 final is tomorrow in this classroom. We decided to put it at 6 a.m.
6 a.m.
You're gonna be like, what? No.
Because let's say you're going out of town. Say that Professor Cook is going out of
Say
town.
like 7:30. Like he decided to give us an extra half.
Did you guys understand how to do this one? So what you want to do is multiply this out and collect everything that's a coefficient of x to the 6th. Whatever that is, it'll be equal to the 6th derivative of f divided by 6 factorial. So pretty much you need that. You can go back up to this one maybe and see, I don't know. But again, I will write the solution out. I'm sorry I haven't already. The reason this wasn't a power series is the power series has what form? Yes, x minus something to the n or to the k, right? And so the trouble here is the 2x, so you have to factor the 2 out. And yeah, so this would be, minus 1 to the n, 2 to the n, divided by n plus 1, x minus 3/2 to the n. I mean, that's the power series. So you can see the power series is centered at 3/2, and past that I can't say. I haven't worked out yet. But that's the first thing, though. Now it's a power series if you rewrite it like that. Yeah, then you use ratio test and then check the endpoints after that. Let's see here. Converges because it's essentially p equals 2. Converges because it's an alternating series with terms that goes to 0. Diverges because it looks so much like the p equals 1 series. That's very informal, but I think you could do direct comparison to the p equals 1 series here. And this diverges by the jth term test, because as j goes to infinity, that goes to pi over 2. Problem 17. Oh. 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 So the sum k equals 0 to infinity of a sub k is equal to the limit as n goes to infinity of the sum k equals 0 to n of a sub k. But I gave you that the nth partial sum was what? N plus 1 over n plus 3. Which means that the series converges to 1. So that's the sum of the series, 1. What are the terms in the series?
1/3.
It starts out at 1/3. 1/3, yeah. But I want the formula for a sub k. So what you do is you take sk minus sk minus 1. Let me do. I'll calculate a sub n instead, and then we'll change the n to k and make it less weird. Now this, you may have forgotten, but we did this back in our derivation of the nth term test. Remember, the nth term test followed from this calculation that the a sub k was actually the difference of the nth and the n minus 1th partial sum. So that's why as n goes to infinity, a sub n has to go to 0, because both of these partial sums go to the same sum if it converges. So you can't have a sub n not going to 0 if it's convergent by this calculation, actually. So this is just straight up a sub n. So if you took the difference with that at k and that at k minus 1, that would be the formula for a sub k. This is a nasty question for the final if I haven't asked it before. But this is the second time at least that I've talked about this semester, possibly the third, because I think I had it in admission. So this here, see, this is the reason part of the reason I like differential equations for the final is it gives me a way to get like, you know, I don't like the final to be too long, so one thing I can do is to put more than one egg in one basket, you know. And so this problem has, yes, it has separation of variables, but it also has what? Terrible integration, yes. The integral of cosine to the 4th and the integral of inverse sine. Now, inverse sine that's like the first example of integration by parts, right? Because anytime we think about integral of an inverse function, we should think about integration by parts. So like integral of inverse sine, we say, okay, well, that's my u, that's my dv, so I get uv minus integral of v du, which is x inverse sine x minus the integral of, well, x dx over the square root of 1 minus x squared, which, by the way, is x inverse sine x minus 1/2 natural log. Oh, wait a minute. I'm an idiot. No. Just, I guess it's just square root of 1 minus x squared, yeah? If I differentiate that, I get 1 over 2 times the square root of 1 minus x squared times the derivative of the inside function, which is minus 2x, which gives me the minus that I want, but I think I need a plus here. Anyway, something like that. This is roughly it. How do you integrate cosine to the 4th? Break it into two different identities, right? This is 1/2 of 1 plus cosine 2